In this video, we're going to begin to learn about a large group of chemical reactions. So actually two groups. So one of those groups of reactions is called substitution reactions, and the other group is called elimination. And we're going to start our discussion by thinking about a specific type of substitution reaction called the SN2. And you're already a bit familiar with the SN2 from learning about the elementary steps that are common in the reactions of organic molecules. So we're going to be using that as a starting place for our discussion today. So our learning goals are pretty simple. We want to predict the products of substitution reactions. We want to provide curved arrow mechanisms for SN2 reactions. So we're going to really be leaning into drawing mechanisms, so these curved arrow mechanisms, and predicting the products of all the reactions that we learn from this place forward in the class. And then we'll think about the relative rates of SN2 reactions. So again, SN2 is a type of substitution reaction. And the reason that we're talking about substitution and elimination reactions together is because there's often a competition between them. So there could be a substitution or there could be an elimination. And understanding what factors affect how fast an SN2 reaction occurs will help you make predictions. Oh, it's a substitution. Oh, it's elimination. But that's a long-term goal. This is what we're getting at today to start with. So obviously we're going to need to know what is an SN2. All right, SN2 reactions can occur on alkyl halides. So we'll just start with a few fun facts. Here are some common alkyl halides with which you might be familiar. So pesticides tend to have alkyl halides as functional groups in them because they alkylate important molecules in bugs' bodies and then they die. Pharmaceutical agents often contain um, alkyl halides, often fluorine, because it changes their solubility properties and helps them cross, say, the blood-brain barrier, as this antidepressant does. And then finally, this might be one that you didn't predict. Sucralose, which is Splenda, has a bunch of alkyl halides in it, and quite frankly, that makes me a little nervous. And you will not find me drinking anything with Splenda in it. And if you're thinking, well, why does it make her nervous? There's alkyl halides. Well, you'll soon know. Okay, we're going to review how to name alkyl halides. So at this point, I would really like for you to pause and name each of these molecules. Excellent work. Welcome back. Just be sure that you recall the rules for naming substituted alkanes, which is what an alkyl halide is. We can go through a few things. I think that the 2-bromopropane is pretty straightforward, though if you have any questions, definitely email me. For the 5-iodo 2,5-dimethylheptane, the second example here, we do want to number the chain so we get the lowest numbers possible. So 525 is lower than 363. So then we want to list iodo before methyl, because iodo comes before M alphabetically. We do alphabetize by the M in methyl, not by the D in di. And then the last example, we have S5-chloro-2,3,3-trimethylheptane. That is a fun one. For this, we do want to give the configuration of the stereocenter. And so to do that, we have to prioritize the 4 groups that are on the chiral center. So the chiral center is, I'll put a star next to it, it's carbon number 5. So I'll put a star next to it, carbon 5, that one. We go by atomic number, so chlorine is the highest priority, hydrogen is the lowest priority, and then this substituent ends up having higher priority than this one. At first, it's a tie, right? The 2 carbons are tied because they're both carbons. So you look at what they're bonded to. So this one's bonded to H or C, HH. So CHH. This carbon, carbon 6, it's bonded also to C, and then the 2 implied H's, so CHH. You go out again, so now we have to go out one more atom. This is a fun review, huh? So it's these 2 atoms, and then you can definitely see this atom is going to win because it's bonded to C, C, C. whereas we have HHH. All right, we have to make sure that we put the name or the stereocenters configuration in the name. So we've assigned all of our priorities. We trace the path. So 1, 2, 3, and that's what I'm doing here. That's going clockwise, so that would be R, but our lowest priority group, hydrogen, is coming out at us. So opposite day, it is actually S, which we put into the name. All right, awesome. So we can name, super. What's even more important today is that we remember substitution patterns. So when we're talking about alkyl halides, we are very interested in the carbon bonded to the alkyl halide. So these carbon atoms here, these are referred to as the alpha carbon of the alkyl halide. Now this can be a little bit infuriating because the alpha carbon, what is referred to as the alpha carbon, will actually change depending on what the functional group is. But for alkyl halides, the alpha carbon is the one directly bonded to the halogen. And we're interested in their substitution patterns. So the least substituted of the alkyl halides would be a methyl halide. And the methyl halide has its alpha carbon bonded to 3 hydrogens. As we get more substituted, we can take a look at the primary alkyl halide. So the primary alkyl halide has that alpha carbon bonded to one other carbon. So there's one R group here, right? R means alkyl. And so if there's an R group, then that means that that alpha carbon is bonded to one other carbon. Then we can think about secondary. For the secondary alpha carbon, it's bonded to 2 other carbon atoms. For the tertiary, the most substituted alkyl halide, that alpha carbon is bonded to 3 other carbon groups. So this is what we refer to as the substitution pattern of the alkyl halide. It's the number of other carbon atoms bonded to the alpha carbon. So let's go back and look at these alkyl halides that we named, and let's identify the substitution pattern of each of those alkyl halides. A first step is just to identify the alpha carbon. And again, the alpha carbon for an alkyl halide is the one directly bonded to the halogen. And then you want to ask how many other carbon atoms is the alpha carbon bonded to. So for 2-bromopropane, that alpha carbon is bonded to 2 other carbons, and then there's an implied hydrogen. So that carbon is secondary. This is referred to as a secondary alkyl halide, or I might abbreviate it secondary RX for alkyl halide, or we could be super specific and write RBR, alkyl bromide. Excellent. So for our next example, we have a tertiary alkyl halide. That alpha carbon, the one in yellow, is bonded to 3 other carbon atoms. So this is a tertiary alkyl halide. So I might write it's a tertiary RI, a tertiary alkyl iodide. Finally, for the last example, for our chiral alkyl halide, this is a secondary alkyl halide. That alpha carbon is bonded to 2 other carbon atoms. So secondary alkyl halide, specifically, it's an alkyl chloride. And it's chiral, and that might matter to us later. All right, excellent. So you want to be able to identify the substitution patterns of alkyl halides. So let's get to it. So let's think about the reactions of alkyl halides. There are 2 main classes of reactions that are important for alkyl halides. And again, these groups of reactions are going to be in competition, and that is why we're discussing them together. So these are often going to be in competition with one another. But we'll get to that later. We'll get to worrying about that later. So for now, let's look at substitution first and then elimination. So substitution involves replacing the halide with some other group. And that some other group is going to be Y. Y is some nucleophile. It's electron rich. And it will react with the electron poor site on the alkyl halide. So this carbon is electron poor. And so we're going to have the alkyl halide react as an electrophile. Okay. And I'm not going to draw a mechanism here because there are actually two different mechanisms by which this reaction can proceed. And that's the topic of this week. So here's the product. So this is our substitution product. And then you might say, well, what happened to bromine? Well, it actually leaves. And so it has left. And we call it the leaving group. All right. So alkyl halides can react by substitution, where you replace the halogen with some other group. The halogen becomes a halide and it leaves. And this is all happening at the alpha carbon. The alpha carbon, the electron poor site, that is where the action is happening in the substitution reaction. And at least we're part of the actions happening in the elimination reaction. So let's take a look. So elimination reactions are going to look pretty similar. Instead of a nucleophile, we have a base, but besides like B versus Y, bases and nucleophiles, they're actually pretty similar, and the same species can often act as both. So things can get complicated, but we're going to take it one step at a time. The base is the electron-rich species, and it is going to react with the electron-poor alkyl halide. But this time, we're going to observe an alkene. So the base is going to remove a proton from the beta carbon. And again, we're not going to talk about how right now because there's going to be two types of elimination reactions, two mechanisms. And we're going to get an alkene as the product. We're going to have the conjugate acid of the base, whatever that base might be. And we're going to have a leaving group, which in this case will be bromide. Okay. So we're going to have elimination reactions, we're going to have substitution reactions, and they're going to be in competition with one another. Each of these types of reactions, they can proceed by two different overall mechanisms. So we're going to take those four mechanisms, they're called the SN2, the SN1, the E2, and the E1, one at a time. And today, we're going to talk about SN2. All right, so substitution reactions, we're going to hone in on those. So for example, taking some alkyl halide with some nucleophile to make the substitution product and a leaving group. These substitution reactions, again, they can occur by two mechanisms, and I'll just tell you, those two are called the SN2 or the SN1. We're going to learn one of those possible mechanisms. Mechanism just means how, like how do you make a substitution product? We're going to learn one of those mechanisms now, that is the SN2. So let's do it. So we've actually already discussed the SN2, and so I would like for you to go ahead and pause and provide the curved arrow mechanism for the reaction between these two molecules. It occurs in a single elementary step, one that we've already discussed, called the SN2. All right, so the alkyl halide here is going to be our electron poor species. It is going to react as the electrophile, and it's going to react with its LUMO, which is sigma star CBr. It's going to react with the electron-rich nucleophilic cyanide that's going to donate its non-bonding electrons. And now you might ask yourself, well, which atom reacts? Is it carbon or is it nitrogen? Well, carbon has higher energy electrons than nitrogen. And so we will see reaction from carbon. So these electrons on carbon will attack sigma star CBr. Filling sigma star breaks the sigma bond. Also, you can't make 5 bonds to carbon. And so we will end up here with the substitution product and the leaving group.
We can think about the orbital interactions for this reaction. So again, we have this pair of electrons in the non-bonding orbital on carbon attacking sigma star CBr from the carbon side. And we can think about this two ways. We can think about this because we know that an anti-bonding orbital is bigger on a less electronegative atom and carbon's less electronegative. Or we can think about the polarization of the carbon-bromine bond where there is a partial positive on the carbon atom. So we have non-bonding carbon as the highest energy filled molecular orbital of cyanide attacking that sigma star CBr, which is the LUMO, the lowest energy empty orbital of the alkyl halide. And the orbitals do line up like this. This is called symmetry allowed. Fancy words here. So this is called symmetry allowed. And it's a symmetry allowed because the orbitals interact with the same phase and they have the same shape. What would not be allowed is if, say, you kind of came in with the nucleophile from here, right? And you were interacting at the node. That would not be allowed. Excellent. So go ahead and pause and make sure that you have internalized the discussion here. Write a generic reaction mechanism for an SN2 reaction. Think about what the rate law might be, or maybe look up what a rate law is in case you forgot. And then consider, why is this reaction called an SN2 reaction? Last chance. So here's the generic mechanism for an SN2 reaction. An SN2 is just a single elementary step. We've discussed it before. It's a pretty common elementary step that we can see in more complex reaction mechanisms, where we have the non-bonding electrons and the nucleophile attacking sigma star CX. Okay, we get our substitution product, and we get the leaving group X minus. Now, because this reaction proceeds by a single elementary step, the rate law is actually kind of simple because you're just looking at everything that interacts in the rate determining step. There is only one step, so it has to be rate determining. So the rate is rate constant K times the concentration of the alkyl halide times the concentration of the nucleophile. This reaction is called an SN2, where S stands for substitution. In this reaction, X, the halogen, is being substituted for whatever the nucleophile is. And this is important and great because you're making a new functional group in the product. Yes, new functional group. N stands for nucleophilic. We reacted the alkyl halide with a nucleophile. And then 2, this stands for bimolecular. The rate law is bimolecular. It's second order, right? There's a second order rate law. It depends on the concentration of the alkyl halide and the nucleophile. It's first order on both of those for an overall second order rate law. Awesome. So now that we have that down, let's draw the reaction coordinate diagram for an SN2 reaction. Once again, I suggest that you try this on your own before I magically pop up the answer. So reaction coordinate diagram, we do know a few things, right? We're going to have energy versus reaction coordinate. We know that there's just one step, so hopefully those things help you out. And I hope you got something that looks a little bit like this, where we have one step. It's a single elementary step, so that's why we have a single transition state. We start with the alkyl halide and the nucleophile. they start to come together to make this bond. Energy goes up, 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 until you get to the energy maximum, which is the transition state. All right, so that's our transition state. Whatever species has the highest energy along the reaction coordinate. Sometimes this is called the activated complex. In the activated complex, we expect that the bonds are half broken and half made. So whatever bonds are breaking in the starting material, those are half broken. And whatever bonds are being made in the product, they're half made. And again, it is the highest energy species along the reaction coordinate. And then we go down, down, down in energy until we get to the products. Now, back to that transition state. It is super important because it determines the activation energy for the reaction. So this energy, the activation energy, determines the rate of the reaction. So it determines how fast the reaction occurs. And we can remember from general chemistry that the rate is inversely proportional to the activation barrier. So a faster rate corresponds to a lower activation barrier. Okay, so faster rate, lower activation barrier. This is very important. And we're going to be thinking about rates because, as we've mentioned several times, SN2 reaction is going to be in competition with other reactions. So the faster the SN2, the more likely that we are to observe it. Excellent. We're going to be thinking about stereochemistry of the SN2 reaction. So let's take a moment and see if we can predict the product of this reaction, including the stereochemistry. So don't worry about the second question yet. I want you to go ahead and predict the product. Really, really try. Even if you're unsure about the stereochemistry, you should still practice predicting the products with the curved arrows. All right, pause, pause, pause. Last chance. Okay, here's the product. So the product, we started out with 100% R bromooctane. So this is a stereocenter. This is also the alpha carbon. This is where the SN2 is happening. So we're going to have attack of the non-bonding electron pair on oxygen. So up hydroxide. Hydroxide is the nucleophile. It's attacking sigma star CBr. And these are the molecular orbitals for all SN2 reactions. We're going to have the HOMO of the nucleophile, which is a lone pair, so some non-bonding nucleophile, attacking the sigma star CX every time, which is the LUMO of the alkyl halide. Okay, and then from here, this bond breaks, okay, and the electrons in that carbon-bromine bond, they're now on bromide, the leaving group. Now, if we start out with 100% R to bromooctane, we actually will get 100% S octane 2-ol, okay? This is called inversion of stereochemistry. Inversion means you started with R and you ended up with S. Or if we started out with S, we would have ended up with R. And this stereochemical outcome, inversion of stereochemistry, it is observed for all SN2 reactions. So we need to understand that. We need to understand why that is. When we have a chiral alkyl halide, we will observe inversion of stereochemistry R to S. Or if we started out with S, we would end up with R. Now, of course, the way that we're going to understand this is through the transition state. So you probably were hoping we would gloss by the transition state and reaction coordinate diagrams, but we are not going to. So if you need to brush up on that topic from Gen Chem, you should certainly do so. So we're going to think about the transition state. Keep in mind that the SN2 reaction occurs by a single elementary step that I've mapped out here. And what we're going to do is we're actually going to look at 5 species along the reaction coordinate. We're going to start at the starting materials, then look halfway to the transition state, and then downhill almost to products, and then to products. So if you would like to try to draw out what you think those pictures look like, that would be awesome. Do that now if you'd like. Otherwise, we're going to move on here. Okay, so I have everything here because it takes forever to write, but you really want to stay with me and listen to my words. So we're going to start at the reactants. So for the reactants, we have our nucleophile attacking sigma star CX along that proper trajectory. Remember I mentioned that symmetry allowed thing? The nucleophile has to attack from what we call the back side of that CX bond. That is required. So when I say allowed and forbidden, I'm not being hyperbolic. It is forbidden for the electrons to attack from any other orientation. So that is how the nucleophile approaches the electrophile. Let's take a look now at species 2. So when we get to species 2, the bonds between the nucleophile and carbon, it's just starting to form. And the bond between the leaving group and carbon, it's just starting to break. And that's indicated by that dotted line. So that leaving group here, X, it's just starting to leave, just starting to break that CX bond. Now, once we get to the transition state, which is state 3, here we have our highest energy species. The carbon nucleophile bond is half made, and the carbon leaving group bond is half broken. And what's kind of cool here, and what's really important for this idea about what's happening with stereochemistry, is that the substituents on carbon, everything other than the leaving group and the nucleophile, they're actually coplanar. They're all occupying this plane here. So they started out over here on the left, and now they're all coplanar, occupying this plane perpendicular to the plane of your screen. And then as we go, and it's very cool that carbon's actually sp2 hybridized. Woo, awesome. Topic for another day. As we go to species 4, so just as we're heading downhill to the products, you can see that those substituents, A, B, and C, now they're on the right side. So it's like an umbrella sort of flipping up in the wind. So A, B, and C started out here on the left. They all passed through this common plane, and now they're here on the right. So they've inverted upward like an umbrella in the wind, and when they've done that, the stereochemistry of that chiral center has changed. It started out, for example, R, and when you switch everything over here, it's now S, okay? So that's the key to why the stereochemistry, by the time you get to the products 5, has inverted. Because of this transition state. And in this transition state, you do have this plane of, you do have these substituents A, B, and C being coplanar, and then they flip over to the other side. All right, the nucleophile carbon bond is made at the same time that the carbon leaving group bond breaks. And that's the key here. This is a single elementary step. That was a lot. You might have to listen to that again. Think about that again, okay? That was a lot. We're going to move on. Think about what makes for the fastest SN2 reaction. Now, of course, you might not know yet. That's the topic of the rest of the video, and that's where we're heading. So what makes for the fastest SN2? And we're going to be keeping that in mind as we think about reactions that the SN2 competes with. Okay, because the faster the SN2 is, the more likely we are to observe it. So see if you can fill these questions out. What is a generic SN2? What is the rate law? What does the energy coordinate diagram look like? Reaction coordinate diagram look like? Last chance to pause. Okay, so the generic SN2 reaction is you have an alkyl halide coming together with a nucleophile in one single elementary step, right? This is a one-step reaction, which is great because our reaction coordinate diagram is simple, right? We have one single transition state where we have that non-bonding electrons from the nucleophile attacking sigma star CX, which breaks the CX bond and makes this carbon nucleophile bond. Again, it's called a substitution reaction because you've replaced X with the nucleophile. Then we also have this leaving group. As we think about what makes for the fastest SN2 reaction, we're going to be thinking about these electrons that ended up on X minus from that CX bond. There they are. We're going to be thinking about those electrons a lot. The rate law is little k times the concentration of the alkyl halide times the concentration of the nucleophile. Again, for the reaction coordinate diagram, there is a single elementary step with a single transition state that looks like the one that I have drawn here. Okay, this is our activated complex where the carbon nucleophile bond is half made and the carbon leaving group bond is half broken. And one last note here before we move on. The size of the activation barrier, it is going to determine the rate of the SN2. The smaller that activation barrier, the faster the rate. So we're going to take this sort of one step at a time. So we're going to have three main components here of this reaction. We're going to have the alkyl halide, we're going to have the nucleophile, and then we're going to have the leaving group. We're going to think about each of those three things. Right here they are. Here's the alkyl halide in the rate law. Here's the nucleophile. And then the leaving group, like it's part of the alkyl halide. So all three of those species are going to affect the rate of the SN2. So we'll think about how each one is going to contribute to making for the fastest possible SN2 reaction. And we're going to start with the alkyl halide. So let's take a moment and look at this data and wonder if we can explain the relative reactivity of these alkyl halides to SN2 reaction. So orient yourself to this slide.
What we see here is that the less substituted the alpha carbon, the one that actually reacts with the nucleophile. So the less substituted that alpha carbon is, the faster the SN2 reaction. So imagine taking each of these, the methyl, the primary that has one alkyl group on it to the alpha carbon, versus the secondary, versus the tertiary, right? Imagine taking each of these alkyl halides, treating them with the same nucleophile to make these substitution products. The reaction of the methyl halide would be 1,000 times faster than the reaction of the secondary halide. And the primary halide would be 100 times faster than the reaction of the secondary halide. And the tertiary, it would react so slowly, we wouldn't even observe a substitution product. We wouldn't see any of this. So the less substituted the alkyl halide, the faster the SN2 reaction. So now that we can describe the trend, let's try to explain it. Okay, this is a funny little slide here, but I have a methyl bromide, I have isopropyl bromide or 2-bromopropane that we discussed at the beginning of the lecture, tertiary bromide, and then what's called neopentyl bromide. So if we drew out the skeletal structure, it would look like this, and we'll talk about that in just one moment. Okay, so we're going to be looking at the alpha carbons of each of these alkyl halides. So we're looking at the alpha carbons because that's the one that the nucleophile attacks, right? That's the target atom of the nucleophile. The nucleophile would attack each of those alpha carbons. Okay, now and then we're going to turn it around a little bit so we get the nucleophile's view. So that's what we have here, and we're going to take a look at this set of pictures now. So what we can see is that for the methyl, look at all this space. It's hard to see with the highlighter, so I'm going to just circle it in purple. So this is the carbon atom that's being attacked. That's the alpha carbon. The nucleophile can very easily get into that carbon. Now for isopropyl bromide or 2-bromopropane, here is this smaller space for the alpha carbon. It's much more crowded. These two methyl groups, their electron clouds block or repel the nucleophile. It's much more difficult for the nucleophile to get in there and attack that alpha carbon. They are blocked by these methyl groups here. With terbutyl bromide, a tertiary halide, we can see there's just a tiniest little sliver. That's the alpha carbon. That's all that's exposed right there for the nucleophile to get in there. We have 3 methyl groups blocking the nucleophile's attack. Okay, so that explains why methyl would be 1,000 times faster than the reaction of the secondary, and the tertiary would be so slow that we're not even going to observe reaction. And then I also wanted to show you this neopenyl bromide. It has a very slow SN2, and you might say, well, why? I mean, it looks primary, right? It looks like on that alpha carbon, there's just this single substituent. Well, this carbon is called the beta carbon, and look, it's the beta carbon here is quaternary. There's 4 carbon groups attached to it, and that's called beta branching. And beta branching, which is this big beta branch here, this big thing, it also blocks the alpha carbon. And so that's why we see slow SN2 with what looks like a primary alpha carbon, but it has this huge beta carbon next to it. So, it's even more complicated than just this trim, which I think this part's easy to understand, the primary, secondary, tertiary. But, you have to look at the whole molecule as well, and that's what this example shows us. Well, bottom line here is that the more substituted the alpha carbon, the slower the SN2, because of what we call steric, blocking, that works, so electron clouds repel, of the nucleophile's attack. Okay, excellent. So now we understand that. So we said that we were going to think about 3 factors for the SN2 reaction and what affects its rate, right? We were going to talk about the alkyl halide, we're going to talk about the nucleophile, and the leaving group. So alkyl halide, we understand it. We want to look at the steric profile of that alpha carbon. And the less substituted it is, methyl, primary, those will have fast rates of SN2. Secondary will have slow SN2. Tertiary, don't bother, right? And then you also have to look at the molecule as a whole. And if you have beta branching, that will be slow as well. Let's try to rationalize this with the reaction coordinate diagram. So you should go ahead and try to draw reaction coordinate diagrams representing SN2 with a methyl halide, a primary halide, and a secondary halide. Now, primary wasn't represented in this figure, but of course its rate would be right in between methyl and secondary. Go ahead and try that. And you should get something like this. As you move from the alpha carbon being methyl to primary to secondary, you have a more and more crowded attack, right? The target atom is more and more occluded. And so the activation barrier gets bigger and bigger to reflect that, right? So the more repulsion when the nucleophile is attacking that alpha carbon, the higher the activation barrier and the slower the reaction. Okay, that really does end our discussion about the alkyl halide steric profile. So alkyl halide, check. Again, you might need to re-listen to that. We're going to move on now to the nucleophile. And we're going to think about how the nucleophile affects the rate of SN2. So if you recall, the rate law has the alkyl halide and it has the nucleophile. So the less sterically hindered the alpha carbon of the electrophile, the alkyl halide is, the faster the reaction. But now we want to know how the nucleophile affects it. So take a moment and look at this data. It's really complicated. If we're going to take a minute to talk about it. And think about whether or not you see any trends in nucleophilicity. The nucleophile, of course, is using its highest energy filled orbital to donate electrons into sigma star CX. So the higher energy electrons are going to correspond to the best nucleophiles. And that's what we see. So high energy electrons make for good nucleophiles. Let's take a look at the atoms that are in our excellent nucleophile category here. So carbon, sulfur, and iodine. If we had, there are no phosphorus-based nucleophiles in this list, but phosphorus would also be on the excellent nucleophile list, okay? Now, the good nucleophiles, that seem to be based in oxygen, bromine, nitrogen. And then our poor nucleophiles, where oxygen is also there, right? So chlorine, oxygen, fluorine, oxygen. Hey, look, it looks like oxygen is actually more of a poor nucleophile. So we're going to change that. Why not? Okay, what do we see here? Well, we see a couple of things. And the first one is that less electronegative atoms, carbon, phosphorus, sulfur, iodine, those are our excellent nucleophile. Less electronegative atoms, they have high energy electrons, right? And so they are more nucleophilic. So carbon, phosphorus, sulfur, iodine, that's these, right? And then as you see, nitrogen and bromine, well, they are a little more electronegative. They're a little bit closer to fluorine. And so they are just a little worse, little worse as nucleophiles. And then finally, the super electronegative atoms, fluorine, chlorine, oxygen, they're just poor nucleophiles typically because they are so electronegative. Their electrons are low energy, and so they're not very reactive. Now, all this data here, nucleophilicity, is actually defined as reactivity in the SN2 reaction, and these are relative nucleophilicities. Some alkyl halide was treated with each of these nucleophiles and made the substitution products. The rate was measured, and then the slowest rate, which was the reaction with water, was set to 1, and these are all relative rates. So what we can see is that cyanide is 126,000 times faster in an SN2 reaction than water. Whoa, that's a big difference. Cyanide is a way better nucleophile than water. Cool. Now's a good time to say no, you do not need to memorize these numbers. In fact, I'm going to be super mad at you if you memorize these numbers. I need you to know the trends. I need you to recognize excellent, good, moderate, poor nucleophiles. But we're well on our way to just sort of understanding what makes for a good nucleophile. So if you can just understand what makes for a good nucleophile, you don't have to memorize anything. But definitely do not try and memorize these numbers. They're just for our discussion right now. Okay, what else can we see? So we see that less electronegative atoms have higher energy orbitals. Something that can be a little bit confusing is that we trends. So nucleophiles look like bases, right? They are donating an electron pair. So you can maybe think, oh, maybe basicity parallels nucleophilicity. Well, it doesn't. So in a row, it does. So more basic does correspond with more nucleophilic. But in a column, it's actually the opposite. So iodide is much less basic than fluoride, but it's also much more nucleophilic. So iodide is a great nucleophile, but a poor base. So those trends are opposite. Basicity is just fundamentally different than nucleophilicity. Nucleophilicity, you're attacking sigma star CX. Basicity, you are attacking sigma star XH. You're accepting a proton, and it's just different. And that's the topic for a higher level class. All right, let's see what else we have here. So I want to take a look at some oxygen-based nucleophiles. So let's take a look now at hydroxide versus acetate and try to understand what exactly is going on there. So hydroxide versus acetate. These are both oxygen-based nucleophiles, but hydroxide is much more nucleophilic. than acetate. So why is that? Well, remember, the higher energy the electrons, the more reactive, well, that didn't make sense, guys. And on acetate, we can draw a resonance structure, right? So even though we're comparing O minus to O minus, these electrons on acetate are more stable. And so because it's more stable, because the electrons are delocalized, it's less nucleophilic. Okay, so there's that example. So if there's resonance structures, the electrons are stabilized by delocalization, and then everything else is the same, right? O minus versus O minus. The delocalized electrons are going to be less nucleophilic. And then finally, let's look at one more example of oxygen-based nucleophiles. Let's look at hydroxide again, but this time versus water. So let's do this example over here in the corner. So we're going to have hydroxide versus water. And then how can we articulate the difference there? Well, we have a negative formal charge on oxygen versus a neutral atom. So O minus versus a neutral atom. And the electrons are higher energy when we have the negative formal charge. And so because the electrons are higher energy on hydroxide, it is a better nucleophile. And not just better, right? It's 16,000 times faster than water when you react it with the same exact alkyl halide. So it's actually a much better nucleophile than water. All right, so 3 trends here. The big trend was less electronegative atoms have higher energy electrons and they're more nucleophilic. Second trend, if you have the same atom and with the same formal charge, like hydroxide versus acetate, if you have a nucleophile that is stabilized by delocalization of charge, then it's less nucleophilic, right? More stable, less reactive, less nucleophilic. And then our third trend was that when we had hydroxide versus water, we had the same atom, O versus O, but you had a negative formal charge versus neutral. The electrons are higher energy on the atom with the negative formal charge, and so it was a better nucleophile. And the organizing pattern is that high energy electrons make for good nucleophiles. And of course, this is because the nucleophile is reacting through its HOMO. The H in HOMO stands for highest energy fill molecular orbital. So the higher energy, the better. Excellent. All right, we listen to that again if you need to. So we said, let's take a look, that we were going to look at 3 different features of the of a reaction to figure out how it affected the rate of the SN2. So we've already looked at the alkyl halide. The less sterically hindered the alkyl halide, the faster the reaction. So check. Nucleophile, check. The higher energy electrons, the faster the reaction. And now we need to just think about leaving groups. And I've already sort of given it away. The stability of these electrons that come from the breaking of the CX bond, that will determine how good of a leaving group we have and how it affects the rate of reaction. So the more stable leaving group, the faster the SN2 reaction. Just spoiler alert. All right, that's our last thing we have to do here. Scroll all the way to the bottom. Okay. So what is the leaving group in an SN2 reaction? Well, it's the halogen that's bonded to the alkyl halide, right? So whatever X minus is, that is the leaving group. And sometimes I abbreviate it as LG. Actually, I always abbreviate it as LG. So leaving group, LG. So X minus. Now I have for you some data. This chart's a little bit confusing, but I'm going to help you right now. Here's the leaving group. This would be X. That ends up as X minus. And I already have this chart organized for you with the best leaving groups at the top. So these are the best leaving groups. They'll have the fastest rate of SN2. So not HI, but when I minus is the leaving group. And then down at the bottom, we have the worst leaving group. So we're going to have the slowest rate of SN2 when you say have hydroxide as X or an alkoxide as X. So imagine that you had this, an ether, and you had a nucleophile attacking the ether. That would correspond to having OR as X minus, and that will be the slowest rate of SN2. So then the question is, why? Why is iodide the best leaving group and fluoride, for example, is an awful leaving group? Can you explain it? Yeah, you definitely can. And this one is the easiest one to explain. And so the way we can explain this is because I minus, for example, is more stable. It's a more stable conjugate base. And then fluoride. So the alkyl iodide is much more reactive than the alkyl fluoride, for example. So leaving group ability correlates with basicity. Yay, finally. So the weakest base is your best leaving group. Yes, awesome. Your weakest base is your best leaving group. And that's why we have conjugate acid data here. So if you look at the conjugate acids of each of the leaving groups, obviously the one with the lowest pKa is the strongest acid and the weakest conjugate base. All that's left to do is summarize. So I strongly suggest that you pause and do that yourself before listening to my summary. And here it is. So we'll start with the mechanism. So we have some nucleophile using its highest energy filled orbital, some high energy pair of electrons, to donate N to sigma star CX, the LUMO of the alkyl halide. Now, filling up that antibonding orbital makes the carbon nucleophile bond that's in the substitution product, and it also breaks the CX bond, right? Fill an antibonding orbital, break a bond, and then those electrons end up with the leaving group. Okay, so that's the mechanism. It's awesome because it's a single elementary step. And that simplified our reaction coordinate diagram. We just had one step, right? And here's our transition state. So speaking of that transition state, because of it, we observe inversion of stereochemistry when the alkyl halide is chiral. So if you have some alkyl halide, and it has to be a secondary, right? So we know that that's not going to be super common for the SN2. But if you do have a chiral alkyl halide, we will observe inversion of stereochemistry. R will go to S and S will go to R. And that is because of the orbital requirements and the transition state that we examined. Now, if we think about the rate law, it reflects that single elementary step. So it's the concentration of the alkyl halide times the concentration of the nucleophile and is overall second order. So both the alkyl halide and the nucleophile affect the rate of the SN2. Now let's talk about that. So the first way that the alkyl halide affects the rate of the SN2 is through its sterics. And when we talk about the sterics, we're talking about that alpha carbon, the one that is directly bonded to the halogen, right? So sterics of the alkyl halide. So methyl is the fastest, and then primary, and then secondary is kind of slow, but some of them do undergo SN2, and of course that we can look out for chiral alkyl halides when we have secondary ones. And then I just never, ever, ever want you to predict SN2 on a tertiary carbon. It's just not going to happen. That alpha carbon is just so crowded with all those methyl groups that the nucleophile cannot get in there, and there's just no rate of reaction. Next, nucleophilicity of the nucleophile. Okay, So we really want the highest energy electrons. So carbon makes great nucleophiles. Iodide, phosphorus, sulfur, these have the highest energy electrons. They're the least electronegative of the atoms we're dealing with, and they make for the best nucleophiles. Now, there were some other trends that we took a look at. We thought about formal charge, we thought about resonance, and you guys can handle it. And then finally, the leaving group. So the leaving group is part of the alkyl halide, and right, it's X, and it becomes X minus. Yeah. Okay, and so the more stable of a conjugate base X minus is, the better the leaving group. So if you're comparing two leaving groups, like I minus versus Br minus, for example, you want to think about their conjugate acids. And the conjugate acid that's the strongest corresponds to the weakest conjugate base and the best leaving group. All right, we've summarized. Now we're going to practice. So this video is getting really long, I know, but I want to actually work through these with you so that you can get some good examples of how to process these types of problems. So I see I have an alkyl halide, and I see that I have something that can be a nucleophile. So I suspect that I'm thinking about it, could be thinking about an SN2 reaction. I want to identify the substitution pattern of the alkyl halide because I know that affects the rate. The alpha carbon is primary. There's only one other carbon atom bonded to the alpha carbon. So great, I know that makes for a pretty fast SN2. Now, if I want to predict the products of this reaction, I want to take the electrons from the nucleophile. They're going to attack sigma star Cx and expel X minus. So I'm going to end up with this substitution product and the bromide leaving group. And you can say, where's sodium? It's around, who cares? It's a spectator. Okay, so we made an ester, that's our substitution product, and then bromide is our leaving group. Bromide's a pretty good leaving group. It's a pretty stable conjugate base. All right, awesome. So let's go ahead and try this with the next problem. For the next problem, we have sodium azide. So N3, that's azide or azide, if you please. Okay. And this is a great nucleophile. It's part of why I put it on here. It's great nucleophile. Awesome. So it's going to use its non-bonding electrons to attack sigma star Ci. So non-bonding nitrogen into sigma star Ci. And I got so excited I didn't even think about the alkyl halide. So let's go ahead and think about the alkyl halides. We have a secondary alkyl halide, and it's chiral. Cool. So we have a chiral secondary alkyl halide. In fact, it's shown here as a single enantiomer. If there were two enantiomers, both enantiomers, you would expect plus minus to indicate racemic. But that's not here. So it's implied that's a single enantiomer. And of course, we're going to have inversion of stereochemistry. So I suggest that you go ahead and write the carbon chain exactly the way that it is. And then when you draw in the azide, you can show the inversion. So it's not going to be in, it's going to be out like this. And then we can draw the azide in here. All right. So we started out with the carbon leaving group on in the page, and it ends up out of the page. So you can assign the configuration just to be absolutely sure. If you do that, the stereocenter here is S, and in the product it's R. So I'm not going to pause and go through that, but you should convince yourself that stereochemistry was inverted. And then, of course, we have sodium iodide around as well, iodine being the leaving group and sodium being the spectator. That just came with the nucleophile, right? Because you can't buy a bottle of an anion, so it just comes with its counter ion. No big deal. All right, last example. This time we have a secondary alkyl halide, so secondary alkyl halide, but it's achiral. Oops, and of course this was an alkyl iodide. Okay, so a secondary alkyl halide, it is achiral, and we're reacting it with potassium cyanide. Now, cyanide is a wonderful, wonderful nucleophile, really excellent nucleophile, and potassium is just a spectator because you can't buy a bottle of an anion. So we're going to have the non-bonding pair of electrons on carbon of cyanide attacking sigma star CBr, and that breaks the carbon-bromine bond. And then we end up with this alkyl nitrile. So I had mentioned we have all these fun functional groups that we can form by substitution. And so you've seen some examples of these in this slide. All right, want to be able to predict the products of SN2 reactions. Next, we spent a ton of time talking about the relative rates of SN2 reactions. So we also want to be able to predict the relative rates of SN2. So I would like for you to try this before I go through it. Okay, and a good first step would just be to predict the products of all these reactions and also really think about how they're different. So we're going to take these one at a time. We'll take this first pair. We'll call this example A. So example A, the big difference is the substitution pattern of the alkyl halide. We have a primary alkyl halide versus a secondary alkyl halide. And we know that the less sterically hindered the electrophile, the faster the reaction. So this SN2 between acetate and the primary alkyl halide will occur at a faster rate than the SN2 between acetate and the secondary halide. This attack of the secondary halide, it's more crowded. It's harder for that oxygen to get in there and make that bond. So the first reaction occurs at a faster rate to make that ester product. All right, reaction pair B. So we have secondary alkyl chloride with potassium cyanide versus a secondary alkyl bromide versus potassium cyanide. And you can see in the first example, I didn't even write the leaving groups. I didn't care. I'm just so fixated on carbon, right? But it's the leaving group that actually matters this time. So we have chlorine versus bromine. So for both of these reactions, we'll have cyanide attacking sigma star CX and displacing the halide. So we'll end up with the alkyl nitrile and chloride versus the alkyl nitrile and bromide. And now if we want to figure out what's the better leaving group, bromide versus chloride, we look at the conjugate acids. So HCl versus HBr. HBr is a stronger acid than HCl, and so bromide is a weaker, more stable base. Thus, this reaction is faster than the reaction of the alkyl chloride. So I've spent all that time thinking about pKa's and learning acidity trends because it's relevant to lots of things. All right, last reaction, reaction C. This time the nucleophile is different, right? So when we started talking about reaction rates, we said we can think about every single component of this reaction. We think about the rates. We can think about the alkyl halide and its sterics. How sterically hinder? What's the substitution of that carbon? We can think about nucleophilicity. How high energy are those electrons? The higher energy they are, the faster the reaction. And we said leaving group ability. The weaker base, the more stable leaving group, the better, the faster rate. So we looked at the alkyl halide. That was example A. B was the leaving group. And now example C has to do with the nucleophile. So we want to think about what is a higher energy electron pair? Oxygen on hydroxide? Or is it the electrons in sulfur? Now, I think that this is one of the harder trends to remember, but sulfur is less electronegative than oxygen. And so it has higher energy lone pairs. And so it is a better nucleophile. I know it's really weird because it's a weaker base, but it's a better nucleophile. Basicity and nucleophilicity are not the same thing. Okay. All right. To make sure we summarize and reflect. And this has been a really long video, so I'm not going to go through and recap the learning goals. I'm pretty sure you don't listen to them anyways. But listen to this video again and think about, am I able to do each of these things? Good job. This just takes practice.